老师让你接来说，我说我们可以出学分吗？有好处吗？有好处。不能加薪的。学校已经说了，可以加薪的，可以常常改下加钱嘛。
Thank you very much. Thank you very much. I'm very happy to be here to give to give a series of talks. And so my plan is following. So somehow, maybe I don't know whether I can really make it, but the plan. So today maybe I just give you a little bit some introduction, and then probably I can also speak a little bit about the pseudo-holomorphic curves and also stable maps. And then maybe, I don't know whether I can come to the next today, but this is actually naive idea of Lagrangian flow theory. And maybe I indicate some of its applications. So maybe with some applications. And then, but in general, somehow it is not possible to cook up this Lagrangian flow theory. So in general, we don't have chain complex. So therefore, we call it obstructions. And sometimes we can actually rectify this delta so that we can define flow theory. So for that purpose, somehow I have to introduce so-called filtered infinity algebra. And also bimodule, and so on. And then I also have to, study so-called weak Malloy-Cartan equation. In this context, and maybe some homological algebra or homotopical algebra of these infinity algebras. So this is just algebraic part. And then we want to cook up filtered infinity algebra associated with with a Lagrangian submanifold. And then if we have a solution of weak multi-Cartan equation, somehow we can define the chain complex. Or maybe if we have pair of Lagrangians, then we need a bit more condition. So we have a pair of solution of weak multi-Cartan equation so that the potential value coincide. And then we can again define chain complex. So maybe I just want to explain such a thing. So this is just a general story. And then I want to also somehow more explicit computation. So the main example is actually a so-called torus fibers in compact K-rhetoric manifold. And maybe I may also mention so-called the Lagrangian, which is actually appears as a fixed point set of so-called anti-symplectic involutions. Maybe something more, but I don't know. So I just want to provide some explicit examples where we can really apply this to get some explicit result. And if I have time, then maybe I may present a bit more results. So, but I don't know, maybe I may not have this. So this is my plan. So I start with this introduction. And certainly, you may know, all of you know symplectic structures or Lagrangian manifold, but maybe I just fix notation and I just introduce some concepts. So in my talk, actually, usually I denote by X omega symplectic manifold. So this is a symplectic manifold. Namely, this is just a manifold, and omega is a two form which is closed and non-degenerate. Right? So omega is a closed non-degenerate two form. And certainly, all of you know that the easiest example is just even dimensional Euclidean space and equipped with certain standard symplectic form like a dxi, dyi, with I runs from 1 to n. Here this is actually x1, xn, and y1, yn are the coordinate on R to n. Or maybe better to, I don't know, maybe sometimes maybe better to use x1, y1, xn, yn. And so if I use this, then somehow I just identify this even dimensional Euclidean space as a complex vector space. And here we have z1, zn, complex coordinate, and then this zi is just xi plus square root minus 1 y1. So we can just identify this. And in this notation, I identify this R to n with the cotangent bundle of Rn. And it may be a bit strange, but anyway, so I take y1, yn a coordinate here, And then I have a dy1, dyn. It's a frame of the cotangent bundle. And then x1, xn, a fiber coordinate with respect to such a frame. And then, yeah, we can identify these two. Okay, so this is a very easy way. And so typical examples are following. So one typical example is actually cotangent bundles. Of a manifold. Say M. So I have here T star M, cotangent bundle, and here I have M. And then, as I said, if I have a coordinate like a Q1, Qn, it's a local coordinate. And then we have this dq1, dqn, a local frame of this cotangent bundle. And then I denote by P1, that is Pn, just a fiber coordinate with respect to this frame. And then I denote by lambda, it's just a sum of Pi dqi, I1 to n. And then we can easily check that this lambda is defined locally, but actually they match on the coordinate. They actually extend, they canonically extend the coordinate here. Maybe even though, yeah, it doesn't depend on choice of local coordinate Q1 to Qn, right? And so then maybe I denote by omega canonical is just this d of lambda. Okay? Certainly you can also say the following. So if you take this pi, the projection, and then if you want to define lambda and say v, so v is the tangent vector of this tangent bundle. And so maybe I have some point P here. So P is a cotangent vector here. And then yeah, so this one is actually defined as P pi star of V, right? So here I have map like T to pi of P of M, right? And here I have this pi star of V. And so, but our P is actually cotangent vector at this point by definition, right? So therefore we can take pairing of this. So this is this. And if you write it locally in local coordinate, you get this. So therefore, yeah, you have such an intrinsic definition. You can also write it in local coordinate. So therefore, it's actually well defined. So this is this picture. And for this, actually, if you have a Kähler manifold, I don't know, maybe X, maybe J, and this G, and this is a Kähler metric. This is a complex structure, and this is a Kähler metric. And then certainly you can define this omega. So this is actually Kähler form. This is a Kähler form. So if I define this V1, V2 by this G of J, V1, V2, then the condition for the metric is Kähler is nothing but the closeness of these two forms. So therefore, yeah, it's closed by definition of Kähler condition. And this is non-degenerate because G is non-degenerate and J is also and automorphism of the tangent bundle. So therefore, this one gives us symplectic structure. So we have this cotangent bundle example, and also Kähler manifold example, and we also have more examples. But anyway, so these are basic examples. And next, I just fix a notation for Hamiltonian vector field. So let H be a function on the symplectic manifold. And then I denote by xh, it's a vector field on X. So maybe it's not so good to use the same X, but okay, but anyway, so, and then what I say is I of x sub h of omega is equal to gh. So if, so we define this vector field by this condition. Namely, because omega is non-degenerate, so therefore, in this case, if I consider the interior product is a mapping from Tx to T star x, Tx to T star x, interior product of omega, Maybe this is too small, so therefore I may just write here. So okay, so I have this Tx and then T star x, and here I have interior product and then omega here. So I have vector v, and then I map it to this omega and v of something, and then I can plug in some tangent vector here to get the real number. So therefore, this one is a cotangent vector. So this is actually isomorphism of vector bundles because this one is non-degenerate. So if I have a vector field, then I have a unique one form. So I have a vector field, and then this is a one form, right? So this is one-to-one correspondence, one form, and tangent vector field in one-to-one correspondence. So therefore, I have function h, I have this, and so therefore, so this is Hamiltonian vector field. And yes, so in this case, it has in this setup. So here, if gamma is an integral curve of this xh, then this h composed with gamma is actually constant, right? So because if you differentiate this, then you actually have omega and xh, but omega is two form, and so if I plug in xh both sides, and then this is 0. So therefore, we have this is constant. So the Hamiltonian is constant along the trajectories. So the next thing is that Hamiltonian diffeomorphism or Hamiltonian isotopy. Diffeomorphism or maybe isotopies. Okay. So now I have H, which is a function on the real line times symplectic manifold X. And then for each T, maybe with compact support, for simplicity. And then I define this H sub T of x by h of t of x. So I just plug in t in the first entry. And then I have a function, right? So ht is a function like this. So therefore, I have a corresponding Hamiltonian vector field. And so I have a one-parameter family of a Hamilton vector field. Then we can integrate it because this has compact support in x direction, even this integration. And then we get certain isotopy. Maybe I denote by this. So namely this one is the following. So I have phi h t of x, and then I fix x, and then it's a curve parametered by t. So I just take its velocity vector, and then this one is equal to this x sub ht of this phi h t of x. So this one is the integral curve of this. Okay? This. And another condition is that if t is equal to 0, then this is identity. Okay? So you have a one-parameter family of smooth vector field, smooth one-parameter family of vector field, and then you can integrate to get some isotopy, and we call it Hamiltonian isotopy. Maybe generated by this capital H. And so now I have phi, just a diffeomorphism. And phi is called Hamiltonian diffeomorphism by definition. If there exists some function capital H like this, so that this phi is written as a time one map of this. So this is Hamilton diffeomorphism. Unfortunately, the definition of Hamilton diffeomorphism is, not so concise. I mean, not so short. I mean, this. I need this to define this. And so, but we have a wider class of diffeomorphism, so-called symplectic diffeomorphism. So that is this. Phi is a symplectic diffeomorphism. And so this is by definition, right? Definition is just phi is already diffeomorphism, and then this preserves this. So this is very easy to define. I don't need so many stuff. I just write this. But for Hamilton diffeomorphism, I need this. And one of the things is that this Hamilton diffeomorphism is actually symplectic diffeomorphism, because so if phi is Hamilton diffeomorphism, then phi is a symplectic diffeomorphism. So this is just coming from this Cartan's formula. Okay, so this is just using Cartan formula, you can just easily solve this. Okay. So this is Hamilton diffeomorphism. But also I want to say the following. So if you have flow on the manifold, which may be time dependent, then you can construct some time independent flow on R times the manifold, right? So here I can also do the same thing. So if I have this capital H, and then I have a family of Hamilton vector field like this. Now I want to consider this h times, no. Then I want to consider, so this is a Hamilton vector field on X, right? And then I consider X times, in fact, T star of R here. So I define the function K by the following formula. So here, the coordinate here is X, and I denote the coordinate here. T is a base direction, and tau is a fiber direction. And then I have this K, X, T tau. I define it as tau plus H, X, T. Okay, so I define K in this way. So now this T is a coordinate of this manifold. So therefore, this one is now time-independent vector field. Right? Time-independent because T is already included here. So if you write this xk, then I think this one is equal to xht. So this is in this x direction, so in this tx direction. And for this t star r direction, I have d dt plus minus maybe dh, sorry, yeah, okay, dh dt of dd tau. So tau is a kind of new coordinate, right? We have x and t. So tau I introduced now. And then here, yeah, this is just the original vector field, and this is just the translation in t directions. And then I have some tau directions. So from here, I can cook up this. So somehow I can put it in. I can make it a time-independent one. It doesn't really help us so much usually, but I just want to tell this.
Could I ask something stupid?
Yes.
In physics, with S something tau plus with h,
Mm-hmm.
they always argue about the dimensionality. I mean physical dimension, that kind of thing. Could we see
Yeah. So I don't know. In this case, I don't know the dimension of this. Yeah, maybe for that, in that sense, actually, I don't really know. But so anyway, I just wanted to say this, and then yes. So this is just one small stuff, but I may just mention this. Okay, and then the next thing is the following. So I have simplex manifold and Hamilton vector field and the diffeomorphisms. And the next thing is about submanifold, right? So submanifold in a simplex manifold. So there are some classes like a so-called isotropic submanifold and co-isotropic submanifold, and then Lagrangian submanifold. It's actually Lagrangian is actually isotropic and co-isotropic submanifold. And then the last one is maybe symplectic submanifold. So this is actually defined the following way. So I just take S inside of this T, so inside of this X, right? It's a submanifold, right? So S is called isotropic if the tangent bundle is contained in the annihilator of this tangent bundle, right? So like this. Maybe I define this a bit later. And then co-isotropic is actually TS. Is contained in TS. Okay. And Lagrangian is actually the case that this TS is in fact equal to this TS. top. And the symplectic is actually TS. And this TS. Top is just a zero section on this. So just a kind of terminology. And what is these things? Annihilator of this guy. So this one is the following. So this one may be V. Yes, V in T x is a tangent vector to x, but restricted to S. Right? And then I have omega and V times W. VW is equal to 0 for any W in the TS. It may be a little bit strange, so maybe I just take some point x here, and then this here is x, and here is x. Okay. And then I don't really need this. I don't really, because x is a point in S. So therefore I don't really need this, but if I drop this x, maybe better to restrict it to S. So anyway, this is a annihilator of TS with respect to symplectic form. And so this is just a condition for the submanifold. These are condition for submanifold. And so the last one is, we can also say the following. So we have omega, and then we can just restrict it to this TS times TS, right? And then this one is non-degenerate. This one is non-degenerate. So therefore it is exactly the same as this. If I have S inside of this X, maybe iota, and then this iota star of omega is actually symplectic form on this S. So the last case actually just restriction gives you symplectic structure on this submanifold. And so we have these things. And I will mainly concerned about this Lagrangian submanifold in this series of talks. But maybe I just mention a little bit about co-isotropic ones. Okay. So let's assume that this S is co-isotropic. And then, by definition, actually, we have this thing. So the tangent bundle contains this. This is actually a so-called subbundle. So therefore, it's so-called distribution of this on S, right? So-called distribution on S. And point is that this one is actually involutive. So this is actually very important, that this is involutive distribution. Namely, if you take two sections of this, and then you can regard them as a vector field, and then you can take the Lie bracket, and that also belongs to this. So this is involutive things. So therefore, from here, we can actually get a foliation, right? We get so-called characteristic foliation. So maybe, I don't know, maybe f of s. So each leaf of this foliation is actually maximal integral submanifold of this series. And so this is just a sort of exercise. If you know the definition, and you just manipulate it. So this is one. And then then we may consider its leaf space. But leaf space may be not so nice, may not be so nice. So you have some bad topological space in general, but sometimes we have a nice thing. So, but sometimes this leaf space is it become a manifold, right? Maybe I can give you one example later. And so then I denote it by this S, and then I just consider these things. So just to collapse each connected integral submanifold to a point, and then I have something like this. I don't know how to denote it, but maybe today I just denote by S under bar. And then this becomes a symplectic manifold. Then this becomes symplectic manifold. And this process is so-called co-isotopic reduction. So maybe I just mention how it is. So here I have S here, and then here I have X, right? And then here I have this S under bar. So maybe I denote by the projection by P, and then this is inclusion by iota. Then there is a form omega bar, and here I have omega. And then we can have some two form omega bar on S bar, which satisfies these things. So you pull back simplex form to this submanifold, you get a two form. And because of this, somehow this two form, restriction two form degenerate along this direction. So therefore, if you collapse this direction, and then you get a non-degenerate one, right? So somehow point-wisely you can just descend it. But the point, it also says that it doesn't really depend on choice of the inverse image of this. So this is also not so, yeah, kind of exercise, but so this is actually this co-isotopic reduction process. So this is the co-isotopic reduction, yes. And typical example is hypersurface. So if S in X is a hypersurface, real hypersurface, and then this S is co-isotopic. And this one is actually easy to see. So let's consider S as a submanifold, a codimension submanifold X. So S can be written locally as a zero set of certain function, right? So locally, you can find some function H, so that DH doesn't vanish. So you have such a defining function, right? And then I take this XH, this Hamiltonian vector field. So this is just one direction in X, but we can see the following. So now I have this. So this is a Hamilton vector field, right? So let gamma be an integral curve of this x sub h, so that gamma 0 start at a point in S. And then I erased. So therefore it's bad. But what I said is some Hamilton function is constant on the trajectories. So, but this h composed with gamma is constant, right? So therefore, h of gamma of t is equal to h of gamma 0. This h of h of gamma 0. So this is actually 0, right? Because this is S and h is a defining equation, so therefore this is 0. So gamma t always on this hypersurface. So therefore gamma t is always contained in this S. That means this integral curve is contained in the submanifold S. And okay, so but because I assume dh is non-zero and simplest form is non-degenerate, so therefore if this is non-zero and then this is never zero, right? So therefore, if I consider this gamma dot of t, so this is a t of gamma t of S and non-zero, right? So now I take another vector, like any vector b from t of gamma t of S, and then consider this omega and gamma dot of t and b, right? And but this one is equal to omega of x sub h of gamma t v. So therefore, this one is equal to dh at gamma t of v, right? But it means that this one is the derivative of h in the direction v, but v is a tangent vector to S. So this one is equal to 0, right? Because h is 0, right? So therefore, we can see that this direction is actually this thing. I have to say this. I have to say one thing. Sorry. Because I define in this way, so this is non-degenerate. So therefore, they are complementary dimensions. So therefore, if it is codimension 1, and then this is dimension 1, and so therefore it is spanned by this. So here, this characteristic foliation is nothing but the integral curves given by the integral curve of these things. Okay, so this is one example I may mention later. And finally, I just remind you some local normal forms. And certainly, you know this Darboux theorem. So if you have this x omega, and then you take some, so maybe I denote the dimension to n, and then take any point p on x, then there is a local coordinate, maybe I don't know, x1, y1, xn, yn, around p, so that omega is actually, in this local expression, actually, this is actually given by this standard one, right? Okay, so this is Darboux theorem. So it in particular means that no local invariant for symplectic manifolds such as curvature in Riemannian geometry. And then this was actually extended for the neighborhood of submanifold of certain type. Maybe this is Weinstein's tubular neighborhood theorem. Maybe later somehow extended by Giventhal somehow, but I just mention one of the very typical case of this. So let's suppose that S in this X is Lagrangian. Okay. His result is actually more general, but anyway, this is Lagrangian. And submanifold. So instead of point, it's a Lagrangian submanifold inside of X. And then there is a neighborhood, a tubular neighborhood, U of S, and a tubular neighborhood of the zero section in the cotangent bundle. I haven't really said that this one is a Lagrangian submanifold, but maybe I just come to this later. So anyway, so I have this S in X, then I take a tubular neighborhood. And then I have cotangent bundle of S. This is also a certain manifold. Inside I have a zero section. And also maybe I don't psi. It's actually a map from U to, sorry. I never give the name, so B of this. So here I have here. It's a diffeomorphism. So V, we have this omega canonical. This is actually D of lambda of this manifold T star F. And here we have this omega such that this omega is equal to this psi star of this omega canonical on this cotangent bundle. So in this case, actually, the model is actually a zero section of the cotangent bundle, and locally, S is look like the zero section in the cotangent bundle. So this is famous Weinstein tubular neighborhood theorem. Okay, maybe this is the only thing I have to say right now. Okay, good. Then I just come to some examples. So I already spent such a long time. Sorry. So I said for simplex manifold, maybe I start from the typical example R to N, and then maybe I also have a T star of M, and also I have a Kähler manifold or something. Right? And so now I consider Lagrangian manifold. So example of Lagrangian manifolds. So in this case, actually omega is just this dxi with dyi, and then maybe I can take Rn. This is just maybe y1, yn is equal to 0. Or maybe you can also consider anything like x1, xn is equal to 0. I don't know, I don't know. This is also Rn, but so a lot of things. Yeah, they just vanish because they are constants. Therefore, this one is 0 or this one 0. So therefore, and for this class, actually I have this T star M, and I have M, and then I consider section here. So section S is nothing but one form, right? S is actually one form, and then this S is a Lagrangian section if and only if this S is a closed one form. So this is because this S as a one form is equal to S star of this lambda, and this S is a one form, and this form is a section. I denote them the same letter, but this is the way. So from this, actually it's very easy to see that this one is an example. And the last one, maybe I can say the following. So like a CPN, I have a RPN in CPN. Okay. So what I wanted to say is this. I erase this, but so here I have Cn plus 1, and here I have Rn plus 1. So this is actually a real part. Real part, I don't know, real locus. Okay. And then inside here, I take S to n plus 1. It's a unit disk, unit sphere. And here, I take the intersection with R n plus 1 intersect with S to n plus 1. And this one is actually S n. No, S. Oh, wait. Okay, Sn, right? Okay. And then here, it's a hypersurface. Therefore, it's co-isotropic submanifold. So we can talk about this co-isotropic reduction if the quotient space is nice space. And in this case, actually, you know the characteristic. And this actually gives you exactly a Hopf vibration here. So therefore, here you have CPN. Right? And here, it's actually, if you restrict it here, so this is after the quotient by U1. And this is actually the quotient by R and U1. So this one is in fact plus minus 1. So therefore here the projection is actually RPN, right? Because this one is Lagrangian, so restriction simply form just vanish here. And then this, if you just look at this reduction process, and then this one also gives you Lagrangian submanifold. So this is this example. And we also have something like this. So if tau is a anti-symplectic involution, namely tau is an involution, namely tau square is identity, and tau reverses symplectic form. Right? If you have such a thing, then we can talk about this fixed point set. So this one is also Lagrangian submanifold. In this example, we just consider the yi mapped to minus yi, and then the fixed point set is actually this yi is equal to 0, and this gives you Lagrangians. So we have such examples, and okay. And another example is the graph of symplectic diffeomorphism. Maybe I also, so another example is phi is a symplectic diffeomorphism. Then I consider gamma phi is a graph, namely it's a p and phi p, and p is in x, right, is a subset in the product of two copies of X. And now I equip this space with the following two form. So I just pull back omega from the first factor and then multiply by -1 and then add with the pullback of omega by the second projection. And then this one is symplectic. And it is easy to see that this one is also Lagrangian. So if you have a symplectic diffeomorphism, you can cook up some Lagrangian manifold. So there are such examples. And so many important objects are actually described as a Lagrangian manifold. Okay. And then maybe I have to stop in 5 minutes. Okay. I think I may be too slow, so I haven't really. Yeah, because this part, maybe most of you may know.
When you rest up, could I ask a stupid question again?
Yes?
I know the precise just rest up is far away from canonical. So the precise, the Weinstein precise is far away from canonical.
No.
So I'm asking how canonical it is.
No canonical.
Yeah,
So,
I know, but I try to see how. And you can, okay.
No. Actually, so in this geometry, somehow, as I said, the symmetry is quite big. Like a Hamiltonian vector field gives you symmetry, right? So it is actually infinite-dimensional ambiguity, right? So no.
So in some sense, the ambiguity is well understood. That's why I'm asking. Or no?
I think it's actually the symplectic morphism of this tubular neighborhood, right? But to understand symplectic automorphism of some domain is not so easy. So not fully understood. But anyway, this is one thing. And finally I want to say something so-called Hamiltonian displaceability, and so this thing, just a notion. So I have X omega, it's a symplectic manifold, and then take A, just a subset. Often we take some closed subset, but it doesn't matter. So if we say that A is said to be Hamiltonianly displaceable, so if and only if there exists phi, it's a Hamiltonian diffeomorphism of this X, so that phi of A displaces A from itself. But maybe I may take closure for one of them, but anyway, like this. So somehow, small one is always displaceable, right? So like if you have R to N, then I have a point here, then I have a coordinate. Like even R2 is okay. So I have here x-axis and here y-axis. And then I take, say, x is a Hamiltonian function. And then I consider this x of x, Hamiltonian vector field of this function x. And then this one is equal to d dy. Right? So therefore, you just do this translation. So therefore, this one. So if you take certain compact subset here, then if you consider big, just to multiply some big number, and then time one map displace it. So this is okay. If you want to have a compactly supported Hamiltonian, it doesn't matter. You just cut off at far away. So this is the definition. And So Lagrangian submanifold sometimes, or most, typically maybe has non-displaceability. Certainly, it is not really true. But for instance, so the typical example is actually one is Laudenbach and Sikoroff. Maybe they prove first. I don't know the order. And then also Hofer also prove this. So if we have a zero section of this, zero section of this cotangent bundle. So because it's closed form, because zero is just a closed form, therefore this one this. And then phi is Hamiltonian diffeomorphism. Okay, so I assume that M is compact, M is a closed manifold. Okay, and then this one is not displaceable, not Hamiltonianly displaceable. In fact, their result is more stronger. I mean, they actually gave a lower bound for the intersection point. So if they intersect transversely, it is bounded from below by some of bit numbers, and that is due to Laudenbach-Sikoroff. In general, you can estimate this number from below by so-called couplings, and that may be also Hofer. Maybe Laudenbach-Sikoroff also have this. So this one is also estimated by certain topological invariant of this n. And their approach is actually so-called generating functions for Lagrangian submanifold. And so somehow you then appeal to certain finite dimension topology to get result like this. And he actually used certain Holomoshikov techniques to do this. And the Floer theory is somehow a continuation of this. Okay, so this is actually Laudenbach and Sikoroff. And but there is another result by Laudenbach-Sikoroff. Maybe it's also I don't know. This one maybe in early 80s, maybe early 80s, I think. This one may be written middle of 90s, so a bit later. So if S, maybe they consider also closed manifold, I think so. But anyway, so you have this X omega. So this is a submanifold, maybe closed submanifold. And let's assume the dimension is just a half of the dimension of the ambient space, like in the case of Lagrangians. So, I didn't say this, sorry. So if S is Lagrangian, so this says that this one is equal to these things. So they are complementary dimension, but there is the same dimension. So therefore, from here, this dimension is just half of the dimension of the manifold. For Lagrangian submanifold satisfies this, but here they also assume this, and then they assume that S is not Lagrangian. And also, S can be displaced by a maybe homomorphism is enough, but maybe diffeomorphism. So S can be displaced topologically. Maybe C infinity sense, but so topologically. So no symplectic geometry here. So no Hamiltonian things. Just to assume this is topologically displaced. And then S is Hamiltonianly displaceable. I mean, maybe by a small Hamiltonian diffeomorphism. So this result somehow characterize a feature of Lagrangian manifold. So this one, if you have a Lagrangian manifold, then the neighborhood of Lagrangian manifold is described by Weinstein's theorem. So you can think of it, it is contained in the cotangent bundle, and then you can just use this kind of result, and then it is not displaceable. And here, certainly there are non-Lagrangian which cannot be displaced by topological reason. But if topologically displaceable, and then this is Hamiltonian displaceable. So this actually can be used to show certain rigidity of Lagrangian manifold in the C0 symplectic geometry. So namely, but anyway, so I just want to give you a little, feeling of this. So let's consider T2, just R2 over Z2. And then I have a coordinate, like a base coordinate, like Q1, Q2, modulo Z, mod Z. So they are the coordinate on the base. And then P1, P2 are fiber coordinate. And then our standard simplex structure on this cotangent bundle of T2, sorry. I consider cotangent bundle of T2. And then our standard symplectic form is equal to this dp1, dq1 plus dp2, dq2, right? So this is standard one. And if you use this, it's impossible to displace zero section by Hamiltonian diffeomorphism, right? This is this result. So now I just change this a little bit. So take any small positive number, maybe any epsilon, which is non-zero, and then I define this omega epsilon by this omega can plus epsilon times maybe dq1 with dq2. Maybe I just assume this is small. I don't know. Probably this is not necessary. But anyway, so we consider this. Then this one is non-degenerate. And non-degeneracy is certainly open condition. So therefore, at least for small epsilon, this is still non-degenerate. Probably in this case, probably we don't really need it. But for simplicity, I just add smallness, and then this guarantees that this is symplectic form. But probably it is not necessary. But anyways, in this case, we can easily find a Hamiltonian diffeomorphism such that this zero section is displaced. I don't know, maybe you can just try to cook up some Hamilton vector field, and then you can see this.
But this has to be this spatial perturbation, like nearby simplex structure. Would this be also replaceable?
So this one, yes.
This is a spatial one, right? If you have nearby simplex structure, then
yeah, so actually what I'm saying is, so zero section, right? Zero section is in this thing, right? So this zero section of this T2, sorry, so T2, only T2 in this case, right? It's a submanifold. And this is Lagrangian with respect to omega canonical, but it is not Lagrangian with respect to this omega epsilon.
So it's,
Because this is the area form.
okay,
So therefore, if it is, we cannot really use this, but we can use this, right? But what I'm saying here is I never use this to prove this. It's very easy to find some function so that you can do this. So this sort of thing somehow quite interesting. And so maybe for co-isotropic submanifold, so this is displaceability things, but somehow this result can be used to get some C0 rigidity. So this one actually gives us certain C0 rigidity of Lagrangian submanifold. And certain type of C0 rigidity of co-isotropic submanifold such a thing is also studied by Humilier and Leclerc and Seyfadini. So in fact, in this case, actually, so probably, yeah, I didn't say this, so therefore it doesn't matter. But yeah, so there are also interesting results. So I wanted to say a little bit about not a proof, but something related to this construction. But maybe I just stop this. Yes. Yes.
So if the collision bundle is already parallelizable,
Hmm?
you just displace the zero section by the translation?
Translation is not Hamiltonian.
It's not Hamiltonian.
Translation is not Hamiltonian. So in this case, actually translation is symplectic, right? But not Hamiltonian. So, but somehow, yeah, in this omega epsilon thing, somehow, you can somehow realize the image is somehow translated in fiber directions by Hamiltonians.
Okay, so in some sense, in this deform symplectic structure, the translation becomes somehow Hamiltonian.
Somehow, yes. Maybe you can just try to find some Hamilton function and then write down the Hamilton vector field with respect to this omega epsilon. And then, actually, it has a vertical component. So, I don't know. Maybe I don't know. Can I spend 10 minutes more? Because okay. Okay. Because I'm always afraid that I'm over time. And often I do this. Okay.
So the condition of Tobacco is equivalent to the self-intersection is zero or not?
So what can you?
Tobacco is pressed.
Topologically displaceable, yes.
Yeah, is equivalent to the self-intersection is zero.
Yeah. So self-intersection is zero. Yes.
They compare, right?
Yes. So that's right. So you have. Yeah. Okay. So. Yes, I think so. Yeah. So just topologically displaceable, and then yeah. I think that's the same thing. Yes.
So what do you mean by the C0 rigidity? What's that mean?
C0 rigidity. Okay. So I have sequence of Lagrange submanifold. It's a sequence of Lagrange submanifold. And then S0, Sn converge to S. If it converges in C1 or C2, and then it's very apparent that simply this limit is also Lagrangian, right? Because yeah, you have a tangent vector actually, right? So let's assume that this S is a smooth submanifold. So all of them are smooth submanifold, okay? So I have a sequence of Lagrangian which converges to a smooth submanifold in C0 topology. Then S is Lagrangian. So if you know so-called C0 relative for Hamilton symplectic diffeomorphism due to maybe Gromov and Erasberg, so you have a sequence of symplectic diffeomorphism, maybe preserving one point, and then if it converges to some diffeomorphism in C0 topology, okay, so it converges to some diffeomorphism in C0 topology, and then the limit thing is also symplectic.
I think they need some condition. So what's the condition for the Lagrangian? Because the contact example, if it's just a graph and the one large, it can become Lagrangian limitless holomorphic.
No. In this one,
So in that one, do you have any condition on the Lagrangian?
no, there's no conditions. They are actually but closed submanifold, closed Lagrangian. Yeah. But anyway, so the proof is somehow, so if you have this, and then you take this Sn, so this Sn may not be topologically displaceable, right? But now I can just consider the product with S1. So this is in X, and this is maybe T star S1. Or maybe you can also replace by sphere, right? So maybe you can also consider this sphere. And then this is just the equator. Okay? And so now you have this. This one is topologically displaceable because this part is topologically displaceable. Right? So if this, sorry. Just consider this. Okay. So let's consider this. And this one, if this one is not Lagrangian, so if the limit is not Lagrangian, then by this theorem, actually it is displaceable. So if this is displaceable, I have a tiny tubular neighborhood that's also displaceable. So if Sn converges to S, then Sn finally, if sufficient large n, Sn actually contained in the tubular neighborhood of this S. And so in the end actually, so maybe the condition is this thing. So it converges to smooth submanifold. And then I have a tubular neighborhood of it. And so this one is diffuse. That means Sn is also displaceable in a tubular neighborhood, in a tiny neighborhood. So
The closed mean compact, or what do you mean by closed?
close compact with that boundary. I think maybe I may check it later, but somehow this is a rough idea. So if we have some limit and then this limit is not Lagrangian, and then I take a product with this, and then you can do this. In fact, Rodenbach graph actually mentions this under the assumption that this, I don't know, yeah, this one is topologically displaceable or something. But anyway, so this is one, yeah, the statement I wanted to say this. And so this says that something similar also holds for co-isolated submanifold. And also you have a characteristic, and characteristic also converges. This also, so there is okay, so maybe I just say a bit more about this. Okay, some result on Lagrange submanifold. So maybe very early day of pseudo-formic curve theory, actually Gromov proved the following. So if I have Lagrangian in the standard symplectic vector space, so this is Lagrangian, maybe closed Lagrangian submanifold, and then L is not exact. So I will explain what does it mean. And this one in particular implies that this H1 of L R is not there. So here exact means the following. So omega is equal to the d of lambda. So lambda is in this case this just xi dyi, or maybe you can also take 1/2 of xi dyi minus yi dxi. Okay, and then okay, then yes. Then this L is called exact Lagrangian. If sorry, I denote this by iota, and then this iota star of lambda is exact. So this is a definition of exact. So, but it's always the remark is that this one is closed. Because if you just do this d of iota star of lambda, and then this is equal to iota star of d of lambda, and then this one is equal to iota star of omega canonical, right? And this is 0 because it's Lagrangian, right? This is Lagrangian condition. So therefore this is closed, but it says non-exact. So that means this iota star of lambda gives you a non-trivial cohomology class in this H1 of R. Right? So this is one result by Gromov. And there are also some other results, like maybe Viterbo. Actually, he proves the following. So if L is it's a closed Lagrangian submanifold, embedded Lagrangian submanifold, not immersed, then L cannot carry a metric of negative curvature. So, yeah, this is one result, and he also proved similar thing for CPN, or maybe more generally, he considered Lagrangian in so-called uni-ruled symplectic manifold, and then they cannot carry a metric of negative curvature. Okay, so they have. He has also a proof of a partial, also so-called a partial result on so-called Collat's conjectures. And then for 3 dimensions, actually Kenji Fukaya also have some result on the 3-dimensional Lagrangian in this R6. And then he can restrict the topological type. So he has a constraint on topological type of this Lagrangian submanifold A. So this is one. Okay. So those, all of them actually using, this one is not, but holomorphic curve technique. And this can be also proved by holomorphic curve techniques. And finally, I want to mention the other side. Okay. So up to now, I said Lagrangians, embedded Lagrangians. So up to now, Lagrangian, if I write this way, up to now I wrote this way, this is actually embedded Lagrangian submanifold. And if I write this way, and then this is the immersed Lagrangian submanifold. And they are completely, they are different features. They have different features. So this Lagrangian immersions this actually more topological, maybe more homotopical argument. So this is so-called H principle. So quite flexible. So for instance, I don't really like this. And certainly we have the following things, like any n. I mean, I have a Lagrangian immersion of spheres. So this you can easily you usually cook if you know the way, you can cook up this. But it is not possible for embeddings if n is bigger than or equal to 2, because of this, right? So another thing is so there is a notion of totally real submanifold. So totally real somehow means that this T of S of J of TS maybe just 0 or something like this. And so we have say C3 and standard complex structure here, right? Then there is a construction due to, I forgot their names. One is Rudin, the other is Ahan. So this is actually totally real embedding. So here, So, but if n is bigger than or equal to 2, then Sn cannot be Lagrangianly embedded in this R2n and omega 0, right? But here, actually, you can embed this sphere in this standard space as a total real submanifold. And you can, so reading also have another paper that Klein-Bottle can be also totally embedded in CT. And now we know that Klein-Bottle cannot be embedded into standard R4. So this, it took some time, but somehow now we know this. So total real thing, Lagrangian thing, yeah, certainly, yeah, have some similar, some common features. Like if S is in the middle dimension, and then the normal boundary is actually isomorphic to the cotangent boundary of this, and that's yeah, in common feature of this. But yeah, they are actually quite different things. So yeah, this is one very early result by Gromov, and which manifest the difference of these two things. Okay. So now I have to stop. So I haven't said anything about holomorphic curves, but maybe in the afternoon I'll start talking about this. Okay. Maybe I want to understand the.
So I show you an example. So I have an example. So at the list this disk. So you can have a family of Lagrangian, but the limit is holomorphic disk. And I think we can make it complete. But your case is closed.
Yes.
Yeah. So I can give you. That's my paper 25 years ago.
Oh, I see.
So I show you.
Okay, yeah.
So probably in different settings. So I'm showing you that it's not a C0 close.
But this is your case also C0 limit is.
C0 limit, but it's a graph. It's a
Yes.
graph. It's not closed. To make it like this boundary. Yeah. So I also need to find out the.
Okay.
Discuss about isotropic structure. You assume the leaf is smooth. Yes. So in general, it's gone.
No.
So we have some kind of resolution of singularity, kind of thing.
No.
It's very complicated.
I don't know. It's very hard space.
Very bad.
Yeah. In principle,